Hello, I'm Martin Fouilleul. I would first like to apologize to the CMMR organizing team for missing the assigned time slot for this presentation, which is entirely due to a mistake on my side. And I would like to thank Dr. Tetsuro Kitahara for being kind enough for allowing me to present in this video. So I will present the work we did with Jean Bresson and Jean-Louis Giavito on a polytemporal scheduler for musical application, and I would like to introduce the motivations behind that work using this photo. This is a photo of a rehearsal for an opera by Karlheinz Stockhausen, and what we can see in this photo is that there are many different actors of many different trades that must all agree on a common notion of time and that must all communicate and synchronize in order to make the show happen. And they do so using several communication channels that can be visual cues, audio cues, verbal instructions, and sometimes computer protocols. So the question we ask is, how can we design tools to help all these actors to handle that complex network of temporal interactions? There has been a number of widely accepted and widely used temporal models in show control applications. You can see timelines, you can see them in most sequencers, for example. You have also queue lists that are nested lists of queues or events with associated timing semantics. So for example, you could have some lists that play each item sequentially, or that play one item at random, or that play items with some timestamp. You can, of course, have hybrids of these two models. And you also have graphical scheduling environments that allow to place events and queues in some abstract space and to draw trajectories between these queues, or to build flow graphs with these queues. All these temporal models mostly map queues to wall clock dates, or they trigger queues based on external input, for example, keyboard inputs. And they either have no notion of symbolic time or one global notion of symbolic time that is shared by all the queues and all the events. Musical time is a little bit more complicated than that. It is, of course, highly symbolic. You can express time using, for example, bars and beats, which are abstract units of time. And musical time is also often deployed at many different scales. So, for example, you could have tempo indications for a movement, and then you can have modifications of that tempo for each sections, for each phrase, for each cells, etc. So we want to build a scheduler that allows arranging computations and commands along abstract time axis, so that you can have all your commands to light systems or audio devices or stage props and so on, and organize all them in some abstract score which deals with multiple related abstract timescales that you can map back to wall clock time using tempo curves or using informations from the live performance. I would like to expand a little bit on this notion of symbolic time or abstract time, and we can take the example of the musical score. So in a musical score, you have an abstract time axis, and you have notes or chords that you can assign to some position in bars and beats. And then you have a tempo indication. Of course, you have to factor in all the interpretative choices of the performers into that tempo. But the point is that tempo defines a time transformation that maps the abstract time of the musical score to the real wall clock time of the live performance that you can express in seconds. So our scheduler expands a little bit on that notion. You can have abstract timescales that are organized in a tree hierarchy. And essentially, the time of a timescale is related to the time of its parents through a time transformation that is specified by a tempo curve. And at the root of the hierarchy, there is the wall clock time. So just to clarify a little bit about the names here, I will call time the time of a parent timescale, so the input of a time transformation, if you will. And I will talk about position when I'm talking about the abstract time of the child timescale, so the output of the time transformation. Also, we define tempo as a position increment per parent increment as opposed to beat per minute. It allows us to separate the concept of tempo from the concept of musical meter. So when I talk about tempo, I talk about a ratio of abstract times. So the figure below shows a branch in that abstract timescale hierarchy. And in blue, you can see time plots for each time scales, and time plots show the position of the time scales as a function of wall clock time. The red curves are the tempo curves, and you can see how the time transformation they apply on the time scales warp the plots. And you can see that we can combine time transformation in that way. Now, how do we define a tempo curve? We specify the tempo curves as piecewise functions, which allows us to have complex tempo curves built from simpler and smaller pieces. And each piece is defined by a start and end tempo and an interpolation mode. So we have two simple interpolation modes, constant tempo and linear interpolation between the start and end tempo. And the interesting thing we had is that we can use parametric curves to define tempo. In our case, we used Bezier curves, but the paper can be used to implement the same thing using any parametric curve as long as it indeed defines a function. Most of the time in a musical score, the tempo is defined as a function of position, but it can be sometimes useful to define it as a function of time, so we can do both in our scheduler. So a tempo defines the rate of advancement of the position inside a time scale as either a function of time or a function of position. So essentially, a tempo curve specifies a differential equation on the position in the time scale. And we have two cases. If the right-hand side of the equation is a function of position, we have an autonomous differential equation. And if the right-hand side is a function of time, we have a non-autonomous differential equation. So we have these two cases to take into account. For a very simple and basic example, we can consider a constant tempo. So it's a function of either position or time, but equal to a constant value. And we can integrate that to get the time as a function of position, which is position over the constant value of the tempo, or the position as a function of time, which is the time times the tempo. We can do the same thing for linear interpolation. So now the tempo is a linear function of position or time, and we can integrate the differential equation to find analytical solutions for the position and time functions. Now we can also specify tempo curves as parametric curves. So no, the tempo is a function of the position or time which describes the same curve in the plane position tempo or time tempo as a parametric curve B. And we can't find analytical solution for that, but we can rearrange our differential equation so that the right-hand side is a function of the components of the parametric curve, bx and by, and their derivatives in the parameter s. So we have decomposed our problem in two steps. And if we want to solve this equation, the first step is finding the parameter s for a given time or position, and we can use a root finding algorithm for that. And the second step is solving the equation in the parameter s. And for that, we use a numerical solver, in our case, an adaptive Cash-Carp solver. And you can see in the figure below an example of a tempo curve that is built with two Bézier curves in red. And you can see how this tempo curve maps the position to the time, that is the blue curve. And the orange stems are the results of the time transformation applied to a regular grid of beats. So you can see that when the tempo increases, the beats get closer and closer, and when the tempo decreases, the beat gets further apart. Now let me say a word about the scheduler API. So we build the scheduler around a cooperative concurrent model, which is based on fibers or coroutine, if you will. And in most musical softwares, when you can place events on timelines, when the playhead reaches the time of an event, it will fire an action and it will essentially call a callback. But since we want to describe long-running musical process with interrelated computation, we would much rather write all our musical process in a single coroutine, and then we can define the timing of that coroutine by inserting weights. And each weight take an abstract time value as input, so we can warp the time of the coroutine by applying time transformations on top of it. We have another notion, which is the notion of task, which is a group of fibers executing in the same time scale under the same time transformation. And we also provide a background jumps pool for blocking operation. Normally, blocking operations such as I/O would stall the concurrent scheduler. So what we do instead is that before doing blocking operation, we send the fiber into a background thread. And then when the operation is done, we can bring it back into the normal scheduling flow. So here is a very basic example of what it looks like in practice. I have my first function, which is my task procedure, which prints hello world in a loop and waits for one symbolic unit of time each iteration of the loop. And then in my main function, I describe a tempo curves with two Bézier curve segments, and I will apply that tempo curve onto my task procedure. So the result of that is that the hello world will accelerate and then decelerate following that tempo curve. So a very, very simple example just to show what the API looks like in practice. So now there are a number of points that are the subject of further work. First, we currently only synchronize coroutines inside a single process. But it's interesting to think about how we could synchronize multiple scheduler instances, for example, between different processes or even between different machines across a network. Another very important point is that you noticed that I talked about synchronization only in the sense of speed synchronization or tempo synchronization. But one very important part of synchronization is obviously the relative phase between performers and between processes. And that's the kind of thing that Ableton Link does, but at the same time, Ableton Link doesn't really allow to have multiple notions of time. So it would be interesting to factor that in and to be able to have multiple notions of time with metric synchronization, which would allow to create interesting polyrhythm, for example. And the last point is that this gets very interesting when we can synchronize tempo to tempo and phase values that would be provided by an external score follower, which would allow to synchronize all our coroutines and all our processes with live performers. So I'd be happy to hear your thoughts about these points. And anyway, thanks for listening. And I will be in the Slack to answer some questions. Thank you.